So after our asymptote exploration, rational functions shouldn't be a lot of note-taking because a lot of this is going to make sense to you. But a rational function is a function of the form f of x is equal to n of x over d of x, where n and d are both polynomials. So we're taking a polynomial and we're dividing it by a polynomial, and that's where we get our rational function from. The domain of f is all x's such that the denominator is not equal to 0. And for rational functions to graph properly, your domain and your numerator and denominator can't have something in common. So we're going to have to find some common factors and simplify first. So first we're going to talk about the horizontal and the vertical asymptotes. Your vertical asymptotes will occur anywhere your denominator polynomial is equal to 0. And we knew that from before, okay? From our exploration. The horizontal asymptotes may be crossed provided that the function is approaching that line as it goes to positive and to negative infinity. So vertical asymptotes will never be crossed. It is possible to cross a horizontal asymptote as long as we approach negative infinity, we're approaching that line, and as we approach positive infinity, we're also approaching that horizontal line. So that's there's always some rule breaker. Horizontal asymptotes can have that exception to the rule. No surprises here. We saw this in our exploration as well. All right, so rules of asymptotes. You know these. The graph f of f has a horizontal or no horizontal asymptotes based on the degrees of the numerator polynomial and the denominator polynomial. So when the degree of the numerator was less than the degree of the denominator, what did we find? Denominator had a bigger degree, higher power. What was our asymptote, our horizontal asymptote? Y equals 0, right? Okay. That was the x-axis, or y equals 0. When the degrees were the same, then what did we do? It's too shy. I know you know this stuff. I have to break out my spinner and call on you. The degrees are the same. What did we do? Yeah, the coefficient of the numerator over the leading coefficient of the denominator. Exactly. Okay. And then when the degree of the numerator was 1 or was bigger than the degree of the denominator, then we had our slant asymptote. And that slant asymptote was found by doing what? Yeah, division. We just divide. And we don't care about the remainder, we just divide them. So these are all things that we explored and figured out through our asymptote exploration. Okay? All right, so plan of attack. If possible, simplify your polynomial function or your rational function. And then we're going to find and sketch the vertical asymptotes. So I always do a dashed line so I know that that's just a guideline. It's going to help me with my graphing. Then we find and sketch any horizontal or slant asymptotes. And then x and y intercepts will often help us to graph it as well. What I typically do is look for the y-intercept. So in other words, let x equal 0 and find out what y is, because that's the easiest point to find. Then we plot 2 points per branch so we can see where things are going. Use an XY chart. You can use functional notation. And then you connect your points with a smooth curve. All right, so here we go. We are to graph f of x is equal to 2x over x squared minus 4. So the first thing we try to do is simplify if possible. What will the denominator of that rational function factor into? Positive and negative 2, x plus 2, x minus 2. Is there any way that either of those factors will cancel with 2x? Nope. So there's nothing to simplify. Okay? But by factoring the denominator, you now know something, right? What are your vertical asymptotes? 2 and negative 2. So x equals 2, x equals negative 2 are your two vertical asymptotes. So let's put in a asymptote here. Another one here. And next we're ready to start talking about horizontal asymptotes. So if we look at that, the degree in the denominator is bigger. So what does that mean? Y equals 0 is your horizontal asymptote. So dash those lines because that's going to be a guide. It's going to help you. Okay? Now, when you get ready to write your domain will always work based on your vertical asymptotes. Okay? It's the range that can be changed. So we're going to wait in our range. So what would my domain be here? What do you think, Jax? What numbers can't x be? It can't have a 0 in the denominator, so what would make that 0 in the denominator? And negative 2. So our domain is just like our vertical asymptotes, isn't it? Only we say all real numbers such that x is not 2 and negative 2. And if we want to write that in interval notation, we can say we're going from negative infinity to negative 2, from negative 2 to 2, and from 2 to positive infinity, all with open brackets, because we can't be 2 or negative 2. Okay? Now, let's hold off on the range for just a moment. Okay? And let's think about what's happening here. So let's do the easy point first. So we said 2 and negative 2 are off limits, but let's find f of 0. Let's find that y-intercept. When we plug in 0 for x, what are we going to get? 0. So 0, 0 is a point in our graph. And that landed on our horizontal asymptote, didn't it? So this is one of those times when it may cross, and we'll see how it goes. So now we'll try some other points. Another point that would be easy to try is a good old 1, because 1's a nice number, usually when we're squaring things and so forth. So let's find f of 1. And that means that we're going to take 2 times 1 and take 1 squared minus 4. So 2 over negative 3 is negative 2/3. When I plugged in 1 for x, I got negative 2/3 for y. Okay, let's try another number. Let's try negative 1. So when we plug negative 1 in, we'll have 2 times negative 1 over negative 1 squared minus 4. So 2 times negative 1 is negative 2. Negative 1 squared minus 4 will get us negative 3. Negative 2 over negative 3, positive 2/3. So can we see what it's doing? It's going to approach that vertical asymptote of x equals negative 2 and approach the other one of x equals positive 2, but never touch it. Okay? Good question. Is it a cubic? Does it look like a cubic because of this x squared? And that part of it is acting like a function that is symmetric about the origin. The whole thing is actually going to be symmetric about the origin. Okay? But we have more to go, because we've only tried things within the negative 2 to 2 range. So now we have to try numbers bigger. So let's try 3 and negative 3 and see what happens. Okay? When we plug in 3, we'll have 2 times 3 over 3 squared minus 4. 2 times 3 is 6, right? 6 over 3 squared is 9 minus 4. So 6/5, right? Give myself some space. So that's 1 1/5. When we're 3 over, we are 1 1/5 up. Can we see what's happening there? As we make our smooth curve, it's going to approach x equals 2, and then approach y equals 0, and never touch them. And now let's plug in f of negative 3. And we'll have 2 times a negative 3 over negative 3 squared minus 4. So a negative 6 over 5 again. So we'll be down 1 1/5. And approach, but not cross. Approach, but not cross. Okay. So symmetric about the origin, isn't it? Now, let's look at our range, because this was one of those few cases where it does cross the horizontal axis, right? The horizontal asymptote. So what is our range here? What do you think? All real numbers, right? Then what'd you say? That's not 0. Okay, so typically that would be exactly what we would say. All real numbers such that y is not equal to 0, right? Okay, but did it get to be 0 this time? It did, because this is one of those exceptions to the rules where it's not supposed to cross it, right? But it did, as it goes to negative infinity and positive infinity, it does approach that 0 but doesn't touch it. So this is one of those few times when it is just plain all real numbers. Okay, most of your others will follow that pattern of whatever your horizontal asymptote is what y can't be. Okay, what questions do you have about this slide? Feeling good? All right, one more of these. then we'll talk about slants. Okay? This time we have x squared plus x minus 2 over x squared minus x minus 6. And our first step is always to simplify if possible. So I see two quadratics. We know how to factor, right? So ask yourself, what does the numerator factor into? And what does the denominator factor into? So Chloe, how does the numerator factor? X minus factors of 2 that are going to subtract to get 1. Good. So minus 1 and plus 2. Okay. And Justin, how is x squared minus x minus 6 going to factor? Good. Which is nice, right? We had to factor it anyway, the denominator, so that we could find out what our vertical asymptotes were, right? Okay. But now that we have factors, we can cancel, right? But there's a caveat, okay? Because when we're canceling these, we actually have to think about our original domain and establish that first. So our domain is real numbers such that x is not equal to what? -2 and 3. Okay? So we have to be careful to make sure we establish our domain based on our original function. Okay? We're going to cancel these, but now we have to also realize that when we cancel those, we're going to have a hole at x equals -2. Okay? So now that we've canceled them, let's put -2 in for x and find out where that hole is going to lie. If we say f of x is now x minus 1 over x minus 3, and we find f of -2, that means we'll have -2 minus 1 and -2 minus 3. -2 minus 1 is -3. -2 minus 3 is, so positive 3/5. So at -2, we'll be up here at a positive 3/5. And we're going to put an open circle there. Otherwise, we'll forget. Okay? This only happens when we can cancel. Okay? So next we're going to look at it and decide what would so we know our vertical asymptotes, right? We've canceled one of them out now, so what's the only vertical asymptote we have? Yep, what makes the denominator equal to 0? X equals 3. So we'll put a dashed line here. Okay. And then we have to say what would be our horizontal asymptote. So we look at our degree, y equals 1, because the leading coefficient is 1 in either one, and so y equals 1 over 1. Okay, so we've dashed those in. Now we've got our guidelines. All right, so next we are going to plot some points, right? So let's think about what's happening here. What would be a good one to plot always? 0. 0 is the easiest number, right? Because all the x's are gone, and we get okay, so when x is 0, y is 1/3. Can we see where this is going? Mm-hmm. So it's going to come through here and get really, really close but not touch, and do the same thing over here. If you want to plot another point, you can, to see how close it gets to where these two intersect. You could try f of 1 or f of 2. F of 1 is 1 minus 1 over 1 minus 3. 0 over anything is 0, right? So when x is 1, we're at 0. Okay, and away we go. So rather than, but remember, we're sketching here. We want to have some, we're using our what we know to create our boundaries with our asymptotes and then sketch a quick sketch. Okay. Now we've got to do something to the right of this asymptote. So 4, everybody okay with that? We're going to find f of 4. So 4 minus 1 over 4 minus 3. 3, right? So when we plugged in 4, we're up here at 3. Can you see where it's going? It's going to get really, really close, not touch. Really, really close, not touch. And we're almost done. The last step is to find the range. Did we cross the asymptotes this time? No. So what's our range? Y can't be 1 because it could be 0, right? It just can't be this value. So all real numbers such that y is not equal to 1. Okay. Now, great question came up last hour or first hour. They said, wait a minute, we also had one other thing that y couldn't be. What other value didn't it get to become? When x was negative 2, what did we find out that y became? Right. So to be completely precise about this, we would also say that it can't be 3/5 as well. Okay. Now, am I going to be a meanie and take off 5 points if you don't do that? No. I'm more worried about you finding that hole and putting it there than making sure that you get that in the range. Okay. So also we would want to include our 3/5. Okay. What questions do you have on this slide? Caitlin, do you need to get up and stretch? You feeling okay? All right. We're good? Okay. Then slants. We learned about slant asymptotes, right? When do they happen? When the degree of the numerator is exactly 1 more than the degree of the denominator. And we find it by dividing and ignoring the remainder. If it gets too cold, please turn it off for me. So we divide, and we don't worry about the remainder. All right, so here's our example. X squared minus x over x minus, or x plus 1. Simplify if possible, right? When we factor x squared minus x, what do they have in common? X, we take the x out, take the GCF out, what's left? Minus 1. Are they exactly the same? No, so we can't cancel. They're not exactly the same factors. So that didn't help us at all. So we should be able to look at this one and immediately know what the vertical asymptote is. -1 equals x. Okay, so we have a vertical asymptote at x is a -1. Okay, so that tells us what our domain is, right? All real numbers such that X can't be negative 1. And there it is in interval form, right? So now we know by looking at this that we have a degree that's exactly one more in the numerator than the denominator. So we have a slant asymptote. How do we find it? Divide. So we're going to take our x squared minus x plus 0, right? And we're dividing it by what goes in here? Negative 1, the opposite of the factor. Drop your 1. Negative 1 times 1. Negative 1 plus negative 1. Negative 1 times negative 2. And we don't even care about that remainder. But now we've depressed it. It was an x squared. It is now x, right? So my slant asymptote will be y equals x minus 2. Which is a line, right? We like lines. We know how to graph lines, right? Looks like y equals mx plus b to me. What's your slope? 1. What's your y-intercept? Negative 2. So we start at negative 2. Put a dot. And then we rise 1, run 1. Rise 1, run 1. Rise 1, run 1. Go down 1. Left 1. And now we have our guidelines. So now it's just a matter of plotting a few points. Okay? So when we're plotting our points, 0 is usually a good one to try, right? So f of 0, 0 in over anything is always 0. So 0, 0. Graph it with a black pen. Okay? Now let's try another one. F of, what other number you want to try? 1. So f of 1. 1 squared minus 1. Oh, guess what? We also get a 0, don't we? So it's doing some kind of a little curve here, right? Then approaching but not touching, approaching but not touching. Okay? We don't know how far it dipped down, but we're not interested in that. We're just quickly sketching it. Okay? And then now we need to worry about our left-hand side of that. So what's a good number to plug in? Negative 2, not negative 1, because it's not possible, right? So f of negative 2 we're going to have a negative 6, right? Negative 2 squared is 4. Minus a minus will get us plus 2 over a negative 1. So we're going to get a negative 6. So when we plugged in negative 2, we're down here at negative 6. And we can see where it's going. Okay? Now these are the ones I won't ask you a range on. Okay? Because I'm not going to ask you to go that granular to figure out exactly where did the y stop, right? And exactly where did the y stop here. So I don't need to know what are these values for y that we want to ignore. Okay? Without a graphing calculator, that would be tedious. There's no need for that. Okay? All right. So your assignment is there. It's on your gold sheet. Got some time to work.